Okay, I see that many of you have attended yesterday's session and some of you haven't. Okay, so the plan was to do some very similar content. So either you can, so I'll try to add some questions which are different from what you saw yesterday, since some of you have attended. But if you had any doubts from yesterday's session or in general any doubts related to the course, this is the time to ask and we can see how we can go about it. And so every Monday and Tuesday there will be a session for this course. And since like a lot of you have seemed to be attending both the sessions, from next week we will probably try to cover different content. So for today there may be some overlap. So yeah. Okay. I hope all of you can see my screen. So we'll start off with something and then we can move on, we can take questions. And so yesterday's, was it recorded? Most probably it would have been recorded and I think you'll get the, okay. So we'll start by looking at some questions which will be very similar to the questions which you got in the assignment 1. And okay. So the first week it covered mostly basic set theory and uh, all of these, right? So since so many of you joined, let me just introduce myself. My name is Harshita and I'm a PhD student at ISSL. Okay, so we will start with this question. So let S and T be two finite sets containing M and N elements respectively. Then you want to find the number of all distinct relations from S to T, right? So let's just recall the basic concepts that you need. So what do we know? We have S and T are finite sets. So we'll usually use this symbol to denote the number of elements of S. It's called the cardinality. And so we have cardinality of S is M, cardinality of T is M. So you want to find the number of all possible relations from S to T. So what is a relation? So a relation is a subset of S cross T, right? And so we first try to understand this term. So if you have a set, okay, let's just look at an example. So if you have, let's say X is 1, 2, and your T is 3, 4. So S cross T is all tuples where the first term is coming from S and the second one is coming from T. So you have 1, 3, you have 1, 4. So you have 1 with 3, 1 with 4, and whatever the other possibilities, 2, 3, and 2, 4. 3, 2, 4. Okay. So this is your S cross T. So let's say your S has, so here what was our cardinality of S? 2. cardinality of T was also 2, and you see that S cross T has 4 elements. So just a general of it. So if you have cardinality of S is M and cardinality of T is N, so can you just say what is the cardinality of S cross T? You can type in the chat box. Can more people respond? So the question is, what is cardinality of S cross T? Given that cardinality of S is N and cardinality of T is N. Okay, so there's one answer which says M. Okay, this I hope it's easy to see because so if your S has M elements, so let's for simplicity let us take 1, 2, all the way up to N. And suppose your T is, it has N elements, let's just take 1, 2, all the way up to N. So when you say S cross T, what are we doing? We're taking 1, 1, 1, the tuple 1, 1, 1, 2, and all the way up to N. Then you do the same thing with the second element of S. So you go 2, 1, 2, 2, 2, all the way up to N. So you see that if you write it in this form, so you take 2, 1, 2, 2, all the way up to 2N. So each row, it has N elements, and if you go on like this, so you will get M1, so it's kind of like a matrix, right? With M rows and M rows and N columns. So the number of entries will be N. Each row has N elements. Each column has N elements. The kind of first question is. Okay. So what was our original question? We wanted to see what are all the possible or the number of distinct relations we can have from S to T. And we saw that a relation is nothing but a subset of S cross T, right? So now you know how many elements the set S cross T has. And a relation is a subset. So basically the question boils down to asking how many possible subsets of S cross T can you have? So the final question boils down to asking, or rather than what are all the subsets, how many subsets can S cross T have? Right? So you know that cardinality of S cross T is Mn. So given a set whose cardinality is known, what are all the possible subsets? So let's again look at it through an example. So you look at, let's say, A equal to 1, 2, 3. Let's take a smaller example. Let's take 1 and 2. Right? So what are all the subsets of it? We just, so you have the empty set, then you have subsets with just one element, and then you have the entire set. So you see that it has 4 elements. So this is the subsets of A, sometimes called the power set of A. It's usually denoted like this. So what we got is if cardinality of A is 2, then the cardinalities of power set of A happens to be 4. We'll look at one more example. Let's take the set B is 1, 2, 3. So let's just list down all the possible subsets of B. You have the empty set. You can take all the sets which contain one element. Then you have sets with two elements. And finally the whole set. So what did we get here? We started with a set of cardinality 3 and we got cardinality of power set is 8. Yeah. So you can see the pattern. So 2, 2 square is 4, 3 and 2 square is 8. So in general, if cardinality of a set A is n, we get cardinality of the power set of A is 2 power n. Right? So a very quick way of seeing this is, okay, I see some hands raised. Is it that you have questions? Any questions? Okay. So if the cardinality of a set A is n, you get that the power set. So one way of seeing this is like, see, a very rough idea of the proof. Let's not say proof. So you take any subset B. Take a subset B of A. So what are the possibilities? Every element of A. So any element A of A. So it is either in B or it is not in B, right? And this is true for every element of A. And how many elements do we have? We have n elements. So that is where this number 2 power n comes. So you can take this. So now let's go back to our original question. So the question was, how many relations are there from S to T? So relation was a subset of S cross T. So it boiled down to asking how many possible subsets of S cross T can we have, and for that we need to know the cardinality of S cross T, which is what we got. So given the cardinality of a set, we know how many possible subsets does it have. Since cardinality of S cross T equal to Mn, the cardinality of all subsets of S cross T is 2 power Mn. So this is the number of relations on S cross T. Number of relations from S to T. So are there any questions so far? Or I mean, if you have any other question also, you can answer. You can type it out or you can raise your hand. not, we'll just move on. Okay, let's look at hmm, let's look at this question. So we have the set S is set of all mn in z cross z such that m minus 1 into n minus 3 equal to 90, right? So we have m minus 1 into n minus 3 equal to 90. So forgetting all these notations, what is it that we have? We have some number a into some number b equal to 90. Right? So let's just rewrite it. A into b equal to 90. So 19 is a prime number. So since 19 is prime, what are all the possibilities for it? So the possibilities are you can have a equal to 1 and b equal to 19. See, how many ways can you write 19 as a product of two numbers? The only thing is you can write it as like plus minus 1 plus minus 19, right? There's no other way to break it up. So, so this is the first possibility. Second possibility is a is 19 and b is 1. The third possibility is a is minus 1, b is minus 19. Fourth possibility is a is minus 19, b is minus. So each of these now what do you know? A is nothing but m minus n, 1. So from here we get a is n minus 1, b is n minus 3. So this determines your m and n. Let's just work it out. So if this the first possibility, it gives m is let's write it the other way. So m is a plus 1 and your n is b plus 3. Okay. So your m is 2 and your n is and so on. So you can get the other ones also. So here your m is right. So you only have 4 possible choices for m and n, or rather the tuple m comma n. So S are set S is 2 comma 22, 20 comma 4, 0 comma 3 and yeah. So the cardinality of the set is 2. Okay. I'll again ask, are there any questions or anything, any other question that you'd like to discuss? Okay. If there are no questions, we'll just go ahead with this. Right. So this says which of the following sets is not a null set. Null set just means an empty set. Right? So you're given 4 sets, and let us look at which of them is not empty. Or let's just look at each of these sets separately. So the first set is you're looking at all rational numbers whose square is 5. So can you type in the chat box? What do you think? How many of you think this is an empty set? Is there anyone who thinks this is an empty set? Anybody? Any answers? Can you have a rational number whose square is 5?
No, ma'am, only irrational square could be 5.
Okay, so somebody claims that, yeah, if a number square is 5, it has to be irrational. Okay, so let's see if we can actually prove this, right? So what we want to say is that there is no rational number whose square is 5. So suppose you have such a rational number. Suppose, so what is rational numbers? It is numbers of the form a by b, where a and b are integers, right? Suppose there is a rational number, let's say a by b, such that the square is 5. So you have a by b square is 5. So what does that give you? A by b whole square, I can write it as a square by b square equal to 5. Then I'll just take this b square on the other side. So what we get is a square is equal to 5 times b square. Okay. Now, I hope you know this, that every integer can be uniquely written as a product of prime numbers. So we will be using this. So you look at this equation, right? Let's just highlight this and keep it. Okay. So what do we know? You know that 5 divides this side of the equality, 5b square, right? So 5 divides 5b square. So your 5 also has to divide your a square. I mean, if you have two numbers m equal to n and your 5 divides n, then 5 also divides m. So that is how. So 5 divides a square. So you have 5 dividing some number square. Right? So like, can it divide the square of a number if it does not divide the number itself? So you can just think about it and see that this does not happen. So this will happen only if 5 divides a. And once you have 5 divides a, you will actually have that 5 square divides a square, right? You can just take an example. So 5 divides 15. So if you look at 15 square, you will have one factor of 5 coming from here and the other factor of 5 coming from here. So you will have 5 square divides 15 square. Okay, that's all we've said. And one more thing I said, I should have mentioned. So we can choose A and B such that if you have rational numbers, let's say 4 by 6, you can write it as 2 by 3, right? So in fact, we can choose this rational number so that the greatest common divisor of A and B is 1. So let's take GCD of A and B is 1. Okay, so what did we get? Let's go back to this highlighted equation that we have. We have that 5 square divides a square, which means that again the same thing. You have two numbers which are equal, and if you have some number dividing one side of it, it has to divide the other side. So this gives 5 square divides 5b square. Right? So we have, what does it mean? This 5b square has two factors of 5 coming in. Right? This 5b square has two factors of 5 coming in. But only one is taken into account here. So the other factor has to come from this b square. So this gives that, in fact, 5 divides b square, and that gives 5 b. So again, similar argument is what we used here. And this contradicts the fact that we have taken a and b with their greatest common divisor equal to 1. So this contradicts the fact that the greatest common divisor of a and b is e. So in fact, we have proved that you cannot have a rational number whose square is 5. So let us just re-look at what we have done. So if you look at the key points of the proof, right, we have extensively used the fact that 5 is a prime number. So let me just point out one place where we used it, probably this one. You can just check that we have used that 5 is a prime number. So the only criteria what we need is that this should be a prime number. So we have actually shown something more general, that if you take any prime number, prime integer, there is no rational number whose square is 6. So if we replace this set A by set of all rational numbers whose square is 7, you still get that that is an empty set. If we replace it with like all those rational numbers whose square is say 11, that is again an empty set. This is, we've just shown something more general. Okay, let's look at the other sets. Here, the second one is we're looking at all those real numbers whose square is 9 and 2m is equal to 4. So, B, we are looking at all real numbers whose square is 9 and 2m is equal to 4. So this is again, you look at this second condition, so that gives you 2m equal to 4, which means m is equal to 2. And so see, when we say and, it means both these conditions should be satisfied. And of course, if m is equal to 2, its square cannot be equal to 9. So this is again an empty set. So B is a null set. Here we got A is a null set. Okay. So the next one is the set of all real numbers such that m plus 8 equal to 8. Right? So, of all real numbers such that m plus 8 equal to 8. So you know that 0 plus 8 equal to 8. Option C. So this definitely contains 0. So it is non-empty. It's not a null set. So we have already found a set which is not a null set. Just verify that the last one is a null set. So again the same thing. You are looking at all those natural numbers whose square is an prime number. So just like what we did in the case A, you can show that this will be a math set. So I'll just take a pause. Are there any questions? So those of you who raised your hands, you can ask if you have any. Okay. Then if not, we'll just move on to the next question. So here we have a set S is equal to 1, 2, 3, and we have a relation on the set. So again, let's just recall a relation is a subset of S cross S, right? So relation on S is a subset of S. So here the subset is given to be the singleton set. So rho is just this one element. The question is this reflexive, is this symmetric, is it transitive, is it an equivalence relation? So I'll briefly explain what these terms mean. So reflexive means see it is a subset of S cross S, right? So let us okay even before this. So let us just draw S cross S. So we have 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 2 2. So when we say a relation is reflexive, what we mean is, so for every element A in S, A comma A should belong to, okay, so we'll call the relation R, so R, the relation R on S cross S is, the first point is reflexive if for every A in S, this belongs to the relation. So if you want to look at it pictorially, if you write this S cross S as a matrix, form like this, it means that all these entries in the diagonal should belong to the relation. Right? So this is your first condition. Okay. So second condition is symmetric. So what does that mean? If you have some element in your relation, then reversing this order, like if you have 1 comma 2, then 2 comma 1 should also belong to the relation. So then B comma A should also belong to the relation, right? So if you look at it in the diagram again, what we're saying is, let's say 2 comma 1 belongs to it. Then you also want 1 comma 2 to belong to the relation. So in other words, if you look at this line, the center, it is kind of symmetric with respect to this line. The uh, hello, is my presentation visible? Okay, thank you. Yeah. So when we say symmetric, it means that, see, what are we saying? If 3 comma 1 belongs, then so should this element. So if you pictorially see it, it's kind of symmetric with respect to this diagonal line. And finally, we have transitive. So this says that if AB and BC are in the relation, so if you have the same ending point and same starting point, then AC is also in the relation. So what this means pictorially, you can think about it. So maybe we can discuss if somebody can do that. Right. So now knowing these definitions and yeah, equivalence relation is one which satisfies everything. So equivalence relation is one that is satisfies all of this. So it is reflexive, symmetric, and transitive. Okay, now let's go back to this relation. So we have a set equal to 1, 2, 3, and we have the relation which is given by the singleton 1, comma 3. So can you just type out what conditions does this satisfy? Is it reflexive? Is it symmetric? You can type in the chat box. Screen is not visible. Okay. Sorry. I'll present again. Yeah, thanks for letting me know. Okay. Uh, I hope it's visible now. If it's still not visible, you can type. If it is visible, it's okay. You can leave it. Okay. So we have got some answers. Not reflexive, transitive. Yeah, cool. It's still not visible, the screen.
It's visible, ma'am.
Okay, thank you. Yeah. Yes, exactly. So it is transitive. It doesn't satisfy the other two because if you look at reflexive, what does reflexive mean? You should have things like 1 comma 1, which we don't have, right? So it is not reflexive. It is not symmetric because 1 comma 3 belongs to this relation, but 3 comma 1 does not belong to it. And transitive. Uh, yeah, so let me write. So rho is not reflexive. So simple reason is 1 comma 1 does not belong to rho. So I hope this symbol is okay. It does not belong to this set. This is not symmetric because this element is in row, but when you reverse the order, this is not there in row. And row is in fact transitive. So you only have one element which is 1 comma 3. So what does transitivity say? That if you have two elements like this, where one of them, the ending or the second coordinate is the same as the first coordinate of the other, then A comma C should belong to it. But our relation just has one element. So this hypothesis itself is not satisfied by any set of elements. So it kind of like trivially becomes transitive. And of course, it's not an equivalence relation because reflexive and symmetric is not there. So I'll move on. If you have any questions, you can just type in the chat box. Okay. So the next question, it is something about the cardinality of sets. So you are given cardinality of S, we are given cardinality of T, we are given cardinality of S union T, and
Hello.
yes, please.
Hello, ma'am.
Yes, sir.
Hello.
Hello.
I'm Sunil speaking. I'm not getting the last example on the relation
Okay.
about the transitivity.
Okay.
For the transitivity, there must be three elements, no?
It
A
is
related
not.
to B and B related to C.
Yeah.
Then A related to C.
Yeah.
But there is only one element in the
Yeah.
set. Then how can it be transitive?
Yes, sir. So, what does transitive say? If we look at this condition, what we're saying is, if you have two elements in your relation like this, looking like this,
Yeah.
then the third element should be there. So, see,
Yes.
what is our relation?
But here there is only one element.
Yeah.
But here there is only one element.
Yes, sir. So, see, what does it say? That if, okay, so suppose you had, let me write it like this. Suppose this was your relation, right? You forget about what we have for now. We'll look at this. So suppose this was there, then what happens? You have, we'll take these two elements, this one and this one. So you have 1, 3 and you have 3, 2. So you have to, you're able to find two elements such that the second coordinate of the first element is same as the first coordinate of the second element. So this should give you 1, 2. Right? We are not saying that for every element we should have elements of this form. As in, we are not saying that we should always have 1, 3, 3, 2 and then 1, 2. But you're saying if you have 1, 3 and 3, 2, then 1, 2 should be there. Here we only have 1, 3. We don't have this 3, 2 or 3, 1 or something like that. Does that answer your question?
So,
Yes, sir. You can go ahead. Is it okay? So the subtle point here is that we're saying if you have elements like this in the relation, then the third element also has to be there.
okay. It means if the relation contains only one element, then it is always transitive.
Exactly. It will always be transitive because you don't even have two elements satisfying this condition. We are saying if you have two elements satisfying this, then a third element of this form should be there.
Okay.
So yeah, you rightly pointed out that if you have a relation which is single one element, it will by theta.
Okay.
Okay. Any more questions?
No.
Okay. So we'll move on to the next question. So we have two sets. One is S of cardinality S, cardinality of T. So the formula is the cardinality of S union T is the cardinality of S plus cardinality of T minus cardinality of S intersection T. So you can see this using a diagram. If you represent it using a Venn diagram. So when we say union, we mean this entire area, right? Maybe I'll color code it. So when we say S, we mean this red area, and T is this blue area, and S into C. When we take cardinality of S plus cardinality of T, you can see that when we say cardinality of S, we are counting everything in this set S, the red part. And when we say cardinality of T, we are counting everything in this set T, which is the blue part. So we are actually adding this, this overlapping part two times when we take it with the red part as well as with the blue part. So if you just want all the elements in totality, you should remove this intersection. So that's where this formula comes from. We can look at, so using this formula, you can directly compute your cardinality of S intersection T by substituting. So your union is given to be 17 equal to 12 plus 5 minus cardinality of S intersection. And that will give you this number. So, so just to get an idea of this picture, we can just take a, let's say, very small example. T is 1, let's say 2, 3, 4. So S union T is union of these two sets, which is 1, 2, 3, 4. Intersection of this. Intersection is 2. So you see that when you add S and T, you're actually counting this 2 twice. That's what was happening in the diagram. It's just what we're trying to do. Proceed. Okay, so this question says that you are looking at all those integers whose absolute value is less than 5. Then what is the cardinality of S? So hope what you know absolute value. If you want to formally define it, it is M if M is non-negative minus M is negative. So to simply put it in simple words, where if you get a negative sign, just remove it. We're taking like the positive side of the numbers. So example, absolute value of 3 is 3. Absolute value of minus 3 is 3. We're throwing away the negative sign. So we are looking at the set S, which is all the integers whose absolute value is less than 5. So what is S? You can have minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and 4. We're looking at strictly less than 5. So this has 9. The next question we have to S is all real numbers such that, okay, let's just list it out. So, oh, sorry, this is all real numbers. So it is so is this notation clear? It's all real numbers between minus 8 and 4. So if we draw the line, we have 0, minus 8, and 4. So every number in this area. So here when I say minus 8 comma 4, we don't mean the tuple, we mean this interval, this entire interval. Here we mean by interval. And t is all the real numbers between minus 2, let's say minus 2 is here and 11 is here. So you have this entire interval. So what is symmetric difference? So let's first understand what is symmetric difference. It's confusing. This and this. Yeah. So what do we mean by symmetric difference? So you have two sets. So pictorially, the symmetric difference is this area and this area. Union of these two areas. So if you want to formally define it, one way you can see from the picture is you're taking the whole of S and T and removing the intersection. Right? So you can see it as S union T minus, this is the symbol for subtracting some side, S intersection T. But you can also look at it another way. So let's draw the diagram again and look at these two parts separately. So what is the blue part? The blue part is from S you are removing elements of T, right? This small portion here is basically after you remove elements of T from S. So you can see this as S difference T, that is the blue part, and the red part is from T you are removing elements of S. So union T difference S. So depending on the question or depending on the context, you can choose which of these two definitions you would like to use. But I hope it is clear that these two are kind of the same objects that we are talking about. Okay, so let's go back to our question. So pictorially we have that S is this set, right? The interval marked in black, and T is this part which is marked in red. So to compare it with this diagram, what would be the symmetric difference? So S symmetric difference, we'll mark it in this light blue. So you're taking this portion, see, you're taking the whole thing, but you're removing the intersection. So it would be this portion union this portion. So, sorry, was there a question? I'm sorry if I didn't hear this, I couldn't hear clearly from this book.
Ah.
Okay. So what is this? This interval. So this would be all those elements which are between -8 and -2. But here -2 is included because in the red portion we didn't have -2. So this has strictly greater than -2. So this would be here. This is the blue portion. Are there any questions? Was it okay? Okay. So let's move on to the next question. Okay. So one more thing. Well, maybe it's better. So you have, suppose you have two sets A and B. So we have A and B. So what is A minus B? So you know that it is all elements of A and you're removing elements of B. So we have A, B, this portion. But if you want to write it in terms of, see, we know unions, intersections much better. So if you want to write it in terms of this, what is this? You have A and you're removing B, or rather you're taking all those elements in A which are outside B. And the word outside B corresponds to taking complement, right? So this is all those elements in A intersection, everything that is outside B. So it is A intersection B complement. With this understanding, let's see if we can solve this question. So we have S and T two sets. So this is just an aside. So here we have S, we have T, and what are we given? We are given three objects. S complement intersection T. We are given S intersection T complement, and we are given S intersection T. So let us mark these three in the diagram. So S intersection T, that is probably the more famous one, which is this one. So S intersection T complement, it's what we saw here, right? So A intersection B complement is that portion in A which is not there in B. So S intersection T complement is that portion in S which is not there in T, so which is this area. And similarly, P intersection S complement is this area. So if you see it, what is given is the sum of these three little parts that we get. The equation that we get is S union T is nothing but this blue area, which is S intersection T complement, union the red area, which is S intersection T, union this black area, which is S complement intersection T. And each of these, they don't intersect, they are all disjoint. So we can actually write it as, since each of right hand side are mutually disjoint, so we get the cardinality is just sum. So each of these numbers is given and you can just take the sum. 12 plus 8 plus 10. So it's already 8 o'clock. We will stop with this. If you have any questions, you can ask. Or if you have any feedback about the session and how you would like it to be done, you can mention that.
Ma'am, can we upload this